In the last section, which was discrete dynamical systems, we defined an iterated map where you keep applying the matrix A in order to get your next time point. And then we saw that depending on the spectrum, i.e. the list of eigenvalues, you can start to understand, well, really, the eigenvalues and the eigenvectors allow you to figure out what the long-term behavior of the system is. We also looked at this interesting thing. I guess here I will go to this plot because I really like this plot. So, I mean, any of those plots would have been sufficient. But if we look at this plot, we have an iterated map, so we only have discrete points, but they draw a continuous line between the points. So that means there is some continuous function that that sort of, in a sense, generalizes the discrete points of the discrete dynamical system. And what it turns out is that the way to produce this is to write the ODE x prime is equal to the log of the matrix times x. But typically, when we talk about linear differential equations, we don't take the log of the matrix. What we do is we have x prime is equal to a times x. And so that is sort of the preface to linear differential equations. Okay, so now let's just read this and then we'll get to the problems and we will be on with it. So this section describes continuous analogs of the difference equations studied in 5.6. In many applied problems, several quantities are varying continuously in time, and they are related by a system of differential equations. Here, x1 to xn are differentiable functions of t, with x prime of 1 to x prime n, and aij are constants. Okay, the crucial feature of the system that is linear, to see that, write it as a matrix equation. A solution of equation 1 is a vector-valued function that satisfies 1 for all t in some interval of real numbers, such as t greater than or equal to 0. Equation 1 is linear because both differentiation of function and multiplication of vectors by a matrix are linear transformations. I like that line a lot. That's really cool. That's a good way to put it. Thus, if u and v are solutions of x prime is equal to ax, then cu plus dv is also a solution. Because cu plus dv, where c and d are constants, is equal to c times u prime, or this is cu plus dv prime. Okay, then we get cu prime plus dv prime, which is equal to cau plus dav is equal to a cu plus dv. Engineers call this property superposition of solutions. Also, the identically zero function is a trivial solution of 1. In the terminology of chapter 4, the set of all solutions of 1 is a subspace of the set of all continuous functions with values in Rn. Standard texts on differential equations show that there always exists what is called a fundamental set of solutions to 1. If A is an n by n, then there are n linearly independent functions in a fundamental set, and each solution of 1 is a unique linear combination of these n functions. That is, a fundamental set of solutions is the basis for the set of all solutions of 1. And the solution set is an n-dimensional vector space of functions. If a vector x0 is specified, then the initial value problem is to construct the unique function x such that x prime is equal to ax and x of 0 is equal to some value x0. All right. When A is a diagonal matrix, the solutions of 1 can be produced by elementary calculus. You basically just integrate like normal. The system 2 is said to be decoupled because each derivative of a function depends only on the function itself and not on some other combination or coupling of both x1 and x2. From calculus, the solutions of 3 are c1 e to the 3t and c2 e to the minus 5t for any constants c1 and c2. Each solution of equation 2 can be written in the form like this, where you factor out the this looks in a sense like parametric vector form from earlier. Is that what it's called? I think that's what it's called. This example suggests that for the general equation x prime equal to ax, a solution might be a linear combination of functions of the form ve to the lambda t for some scalar lambda and some fixed non-zero vector v. If v equals 0, the function x of t is identically 0 and hence satisfies x prime equals to ax. Observe that x prime is equal to lambda v e to the lambda t for equation 4, because you just take the derivative. Since v is a constant vector. So the only real thing here is the lambda. Okay, then ax of t is equal to av e to the lambda t. Since e to the lambda t is never 0, x prime will equal ax of t if and only if lambda v is equal to av. That is, if and only if lambda is an eigenvalue of A and V is its corresponding eigenvector. Thus, each eigenvalue-eigenvector pair provides a solution of x prime equal to ax. Such solutions are sometimes called eigenfunctions of the differential equation. Eigenfunctions provide the key to solving systems of differential equations. Okay, I don't really. No. At this point, the applied stuff of these okay, and then they find the eigen. Okay, that's fine. Okay, then they solve an initial value problem, right? Yep. Okay, then this is the solution to the initial value problem. All right, then they plot it. They also plot the eigenvectors, the straight line solutions, right? Okay. They should. This is actually plotting the direction field is way better. Direction field is less noisy than this, but that's okay. Okay, all right. In figure 2, the origin is called an attractor or sink of the dynamical system because all trajectories are drawn into the origin. The direction of greatest attraction along the trajectories of the eigenfunction x2 is along the trajectory of the eigenfunction x2, corresponding to the more negative eigenvalue. Trajectories that begin at points not on this line become asymptotic to the line through 0 and v1 because their components in the v2 direction decay so rapidly. If the eigenvalues in example 1 were positive instead of negative, the corresponding trajectories would be similar in shape, but the trajectories would be reversed away from the origin. In such a case, the origin is called a repeller or source of the dynamical system. and the direction of greatest repulsion is the line containing the trajectory of the eigenfunction corresponding to the more positive eigenvalue. Okay. They give us this, and then they create the general solution. Okay. Then they do a linear solve to find the constants that satisfy the IVP, and then they get the general solution. When just pretty much just as before. Wait. One of the eigenvalues is positive, the other eigenvalue is negative, so we're going to get a saddle point. A saddle point arises whenever the matrix A has both positive and negative eigenvalues. The direction of greatest repulsion is the line through V1 and 0, corresponding to the positive eigenvalue. All right, decoupling a dynamical system. All right, this actually is pretty interesting. Decoupling a dynamical system. The following discussion shows that the method of examples 1 and 2 produces a fundamental set of solutions for any dynamical system when A is n by n and has n linearly independent eigenvectors. That is, when A is diagonalizable. Suppose the eigenfunctions for A are v1 e to the lambda 1t to vn e to the lambda nt for linearly independent eigenvectors. Let P be the matrix of columns of eigenvectors, and let D be the diagonal matrix with entries lambda 1 to lambda n on the diagonal, so that A is equal to PDP inverse. Now make a change of variable defining a new function y equal to P inverse of x. Wait, what? What do you do? Okay. So wait, so y is really equal to xp. The coordinate vector of x relative to eigenbasis. Okay, fine. So now what we want to do is we want to take oh wait, I did this all wrong. Okay. If we substitute this eq in x prime equal to ax, we get d dt of py is equal to a times p times y. Since a is equal to p d p inverse, we get py d dt py is equal to p dp inverse py. So these cancel, and you get so then we get py prime is equal to p dy. Y prime is equal to dy. Okay, cool. And d is diagonal. Cool. So now we get the change of variable from x to y has decoupled the system of differential equations because the derivative of each scalar function yk depends only on yk. Very cool. That's very cool. So then we can easily write this. So then you shorten this, and you just need to write. So then we get y of t is equal to, like c1 e to the lambda 1 t dot 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 cn e to the lambda n t, where where c1 to cn is equal to y0, and p inverse x0 is equal to p inverse x0. To get x of t, just do p of y of t. Okay, complex eigenvalues. Look at this. Look at this notebook. the spiral actually works. How crazy is it to think that the spiral on a notebook could work? Okay, 5.7, complex eigenvalues. In the next example, a real matrix A has a pair of real complex has a pair of complex eigenvalues, lambda and lambda conjugate. Conj-lam. With associated complex eigenvectors v and v bar. Recall from section 5.5 that for a real matrix, complex eigenvalues and associated eigenvectors come in conjugate pairs. That's only for a real matrix, though. That's really interesting. So two solutions of x prime equal to ax are it can be shown that x2 is equal to x1 bar using a power series representation for the complex exponential function. Although the complex eigenfunctions x1 and x2 are convenient for some calculations, particularly in electrical engineering, real functions are more appropriate for many purposes. Fortunately, the real and imaginary parts of x1 are real solutions because of x prime equal to ax because they are linear combinations of the solutions in 6. I'm not getting that. What? So the real part of v to lambda t is equal to 1/2 the average of x1 and its conjugate. Recall a real n but real matrix, then complex eigenvals come in conj pairs. So assume what is it? It's v e to the lambda t and v bar, this is x2, v bar e to the lambda bar t. It can be shown that You get what? E to the a plus bi t is equal to e to the at times cos bt plus I sine bt. Okay. Um, hence x1, which is this. Whoa, what the hell? Bro, what? Yeah, this is gonna be worth understanding, I can tell. But I need to know how to derive this thing. Okay, this first line actually makes sense because all they did was this. So then you just rewrite this part into this one. And then the v is the only other part of this whole thing. So then so surely this distributes in the way that you want, where v is a vector, so that's fine. But then what do they do after that? They say this is equal to the real part of cos bt minus the m part of sine bt minus, oh, because these i's can't, okay, plus I. So wait, they did this, then they did this. Now they're doing this. I times the real part of v times sine bt plus the m cos. Okay. Okay. And you get y1 of t is equal to the real part of x1 of t, which is equal to real of v cos bt plus, oh, minus the m part of v sine bt times e to the at. And then y2 is equal to the m part of x of x1 of t. All right. Do we want to do this example? I don't really want to do this example. What did they do here? They said next write equation 7 to write. Okay, so they take the imaginary part and they write it as because e to the ix is equal to cos x plus I sine x. Dude, Euler's identity is nuts. All right, the real and imaginary parts of x1 provide solutions. You have to do this whole real m thing. Oh, but this is actually pretty cool. Yeah, because they're real. Complex numbers are crazy, dude. Okay, so I'm going to say yes. Because it has 3 distinct eigenvalues. Write the general solution using complex eigenfunctions. Then find the general real solution. Okay, so this is going to take a bit. All right, so we should work through this. Okay, so let's just say A has lambda 1 equal to minus 0.5. Lambda 2 is equal to 0.2 plus 0.3i. Lambda 3 is equal to minus, or wait, no, 0.2 minus 0.3i. Okay, then we have v1, 1 minus 2, 1. v2 is equal to 1 plus 2i, 4i, and 2. v3 is equal to 1 minus 2i minus 4i and 2, because the complex conjugate. Now, so problem 2 is write the general solution. Okay, so then what we're going to get is we're going to get that sum of ci e to the lambda I t v I. So this is going to be the solution. Y of t is equal to. So then we just have to do that. But we already have all the eigen. So this is actually easy because you just write it as like minus 0.5, or you write it as like C1 times e to the minus 0.5 t times V1 plus C2 e to the 0.2 plus 0.3i times V2 t times V2 and so on. But to find the general real solution is really way harder. I don't like that part. Okay, so I think what it's gonna be, what I think the answer for now, right? What is the exact language they use? Now, right, general real solution. So wait, so what did they write the general solution as? Okay, so I got this. That was easy. They didn't even do 3. Where's 3? Oh, here's 3. So then the general real solution is, yeah, this is what I got. So C1, V1, either, yeah. Then you get, I think so, where these are, this is the real part of x2. This is the imaginary part of x2. I actually think that checks out. X2 or x1 in this case was, let's see, this is x1, right? Okay, I think that's right. Now we can read through the exercises. The 2 by 2 matrix A has eigenvalues 4 and 2. Okay, let A be a 2 by 2 matrix. Okay, IVP. Solve the IVP. All right, the practice problems were enough. I am interested in this section though. We're gonna go on. We're gonna skip 5.8 and we're gonna go to applications and Markov chains. But I'm gonna get some food. So this one only took 46 minutes because I mean I should work through one of those complex ones, but it's all right. Just reading the notes is enough for right now. All right, peace out.